In section 11.2, we want to explore power series a bit more. And the first topic we're interested in is expanding more on topic number or note number 5, which was talking about convergence and divergence and how we could perhaps get an interval for convergence, or maybe it'll be just a specific value, or maybe it'll be all real numbers. We want to see what that would look like. So that's what we're going to do. Now remember, we know about the geometric series. A geometric series, of course, and this in particular one is a times r to the k, but a is 1. You can see that there's no value in front of the r, so therefore it must have been 1. So when we write out the series, it's 1 plus r squared plus r cubed plus r to the 4th, etc., etc. And we know that that sum would be 1 divided by 1 minus r. It's a over 1 minus r is the formula, but a is 1 for us. And that will be true provided that the absolute value of r is less than 1, because it's a geometric series. All right, now let's consider the power series. The power series x to the k, which is very similar to r to the k, right? This is basically the same series. It would be 1 plus x squared plus x cubed, and so on. And that should be equal to 1 over 1 minus x, just like it was for the geometric series, because this is basically geometric, provided what? So when does this power series converge? That's what we need to think about. So what needs to happen? Well, the geometric series converges when the absolute value of r is less than 1. So for us, we would need the absolute value of x to be less than 1. That's what we need to be provided, right? That needs to be the case, because if that's the case, then these two series are one and the same. Or related, let's just put it that way, strongly related. In other words, -1 is less than x, which is less than 1. Right? That's one and the same. Now, what would that mean graphically? Let's look at the graph. And of course, I have it here in a static picture, but of course I have it in decimals. Let me show you. Here it is. So this is that graph, and you can see that, well, hopefully you can see that you have -1, x equals -1 on the left. That's that blue line. And then you have x equals 1 on the right. And then x to the k. So the function is 1 over 1 minus x, right? Well, we said it should be equal to. And it is equal to that function, provided that your values are between -1 and 1, right? You can see the red curve. That's the sum, the power series. And it starts off pretty terrible, right? And then it would get better and better. Sorry, I should never let it go to -10. But it'll get better and better and better as I expand my b, which is the top part of my sum. So as I increase, you can see it's doing a better and better job of fitting. And you can see that red curve, that black curve and that red curve are right next to each other. And of course, the real true power series doesn't stop at 41 or even 50. It'll go to infinity, which would mean that we would fill from -1 to 1. So the red curve and the black curve, 1 over 1 minus x, they overlap and match, but only from -1 to 1. That's our interval of convergence. It's not going to work over here on the left, right? That doesn't work. The power series does not help us over there. And the power series does not help us on the right, but it will help us in the middle, in that between those two blue lines. And that's what we just said right here. We said it had to be between -1 and 1, because those are the values. So drawing that on our picture, just to make sure this is clear, over here, that line is x equals -1. This line right here is x equals +1. And the curve, the red curve, will overlap. And that's that power series. So this power series here overlaps the function. And the function, of course, is 1 over 1 minus x, what we said it should be equal to. So this is f of x equals 1 over 1 minus x. So what we're noticing is that the series from k equals 1 to b x to the k overlaps and matches f of x equals 1 over 1 minus x only between x equals -1 and x equals +1, right? Only in there. And of course, if we let it go to infinity, if instead of b, you actually let it go to infinity, it would completely overlap. The only question is what would happen at the two edges, -1 and 1 themselves. We would have to test that. It just occurred to me, I don't know why I'm saying it starts at 1. It started at 0. It doesn't matter. But I'll also make a note that that series would match f of x equals 1 over 1 minus x completely, right? Because we're not having that completeness because we're stopping. So when you're looking at my Desmos graph, I stop it at, you know, b equals 50 or whatever. So there's still a gap there, and there's actually still a gap up here, but that will go away and it'll completely match from -1 to 1, with the exceptions possibly of -1 and 1 themselves. I'll just say it in intermultiplication. X equals -1 and x equals +1 themselves would need to be tested, because it's possible, but not, well, actually, it's not going to match over here because that's an asymptote, so there's no way. But it is possible over here on the left that maybe that red curve would touch that spot, or maybe it wouldn't. We would have to test it. That's what the interval of convergence looks like. It's the interval where the power series matches the function that you're trying to estimate, but it'll have an interval for which it will work. And that interval will have to be tested both in the interior to make sure it works, but then you'll also have to check the endpoints themselves. It's possible that, say, I need a bracket over on this side or a bracket on that side or something like that. Or maybe there's brackets on both sides, and we would have to find that out. And that's where the real fun is. Okay, so when we have a power series that's in the form from 0 to infinity, c sub k, which is c sub k is just the coefficients. And then they're very particular in some series, but c sub k is the coefficients of the power series. A is the center, right? That's where that is. Then, and you can see the center in our particular graph was at 0. Because if you look at the interval, the center of that interval is 0, right? And you can tell it because you don't see a parentheses right here. It's not x minus 2 parentheses squared. It's just x, or x to the k. So instead of x minus 2 to the k. All right, so the set of values of x for which it converges, for which they overlap, is called the interval of convergence. The radius of convergence is half of that, or well, half of that width. So for example, on our previous page, the interval of convergence, was -1 to 1. Like that. We had a center, which was x equals 0. Right? Because it was just x to the k. So if you look at the series, it's x to the k. So there's no parentheses. So 0 is your center. And we have a radius. Well, if you're going from, let's say, -1 to 1, let me draw the picture. So if you're going from -1 here to +1 here, and your center is 0 right here, then your radius would be this distance right here. That's your radius, right? And the radius would be equal to a distance of 1. right? Half the width of the interval. So if your interval of convergence has a width, right, from the lowest value to the highest value, it's how far apart those values are, then the radius is half of that width. Now, how are we going to find these? How do we find the convergence of a power series? Well, there are some options, and we're going to find them almost exclusively with the ratio test and occasionally the root test. Ratio test is the big one, sometimes the root test. That's how we're going to find these. And what are our options? Well, there's a few options. It's possible that the series converges for all x, in which case your interval of convergence, here, I'll do it right here, the interval of convergence would be negative infinity to infinity. In other words, that red curve and the black function completely overlap for the entirety of the function. That's possible, but that would mean your radius of convergence, I mean, if you're going from negative infinity to infinity, then the radius is infinity, right? That's possible. So that would mean that your interval of convergence is literally from negative infinity to infinity. It's the entire number line, right? And your center is kind of wherever the heck you want it to be, because it doesn't matter because you're going to infinity directions on both sides. Then we could have an interval of convergence, therefore it converges inside and diverges outside. So for example, if you think of a number line, it's possible, and this is what we just saw, you converge from -1 to 1, say, so that's the interval of convergence part, and then you diverge everywhere else, which would be out here. Right, that could happen. And that's the one that we've seen so far. So we had convergence in the middle, and then we had divergence on the two edges. And then your radius of convergence, r, is half of the width, right? So that's that picture up above. So you have a center, and then your radius is right here, right? And you have a center right here, right? Like that. And it's not always 0. I'm just drawing the picture of what we had above. And then the last case that's possible is that you converge only at one spot. You converge only at A. So wherever A might be. So here it is, x equals A. That's the spot where you converge. And then you diverge everywhere else. So the rest of the time you're diverging, except for that one big spot. Okay, so then, sorry, I'm making my number lines dark. So then what's your radius of convergence? It's 0, right? You have a radius of convergence that's 0 because a point has no width, right? There's no from low to high. It just is that single value. So the only spot you converge is at that spot. So those are the three options, and we're going to prove them with the root test, or excuse me, the ratio test, and then occasionally the root test, very occasionally, but most of the time we'll do the root test, or the ratio test, sorry. So we will see that in the next example.